As the scale of large language models, LLMs, continues to expand, an interesting phenomenon has emerged. The communication speed during model training has become a performance bottleneck. Just like a large company, if the efficiency of information transfer between departments is low, even the most capable employees cannot perform at their best. The project we are sharing today has made exciting progress in solving this problem. The intranode communication speed has reached 158 gigabytes per second, almost touching the theoretical bandwidth limit of the H800 GPU. This video is shared from the DeepEP project, open sourced by DeepSeek on GitHub. This is a high-performance communication library specifically designed for mixture of experts Mo and expert parallelism EP. Before diving into the specifics, let's first understand two important concepts. The first is the mixture of experts Mo model, which is a special type of neural network architecture. Its design philosophy is quite interesting, akin to dividing a large company into multiple specialized departments. Each expert, i.e. submodel, specializes in handling specific types of tasks. For example, in a language model, some experts might be particularly good at handling technical content, while others might excel in literary creation. When a piece of text is input, the model intelligently assigns the task to the most suitable expert for processing. Expert parallelism, EP, is the specific technical solution to achieve this model. Simply put, it is to let these experts work in parallel on different GPUs. This is like having various professional departments of a company distributed in different offices, simultaneously handling their respective tasks. However, this distributed working method also brings a key challenge. When different experts need to collaborate, how to ensure that the information transfer between them is both fast and accurate? This is the core problem that DeepEP aims to solve. Its main goal is to provide an efficient GPU all-to-all communication mechanism. This mechanism includes two key operations, dispatch and combine. The dispatch operation is like an intelligent scheduling center responsible for accurately assigning input data to the most suitable expert on the GPU, while the combine operation is like a results aggregation center, efficiently collecting and organizing the results processed by each expert. To make this process more efficient, DeepEP has adopted several innovative technologies. The first is the group limited gating algorithm, a concept that first appeared in the research of DeepSeek v3 and traditional methods. Any input could be assigned to any expert for processing. This high degree of freedom, while significant, leads to substantial communication overhead. The group limited gating algorithm cleverly groups experts, restricting each input to be assigned only to experts within a specific group. This is akin to setting up specialized business groups within an enterprise, where each type of business flows only within a specific group, greatly enhancing efficiency. In terms of data transmission, DeepEP has made detailed optimizations for different scenarios. Within the same server, GPUs are directly connected via NVLink. This is like having dedicated high-speed channels between departments with a bandwidth of up to 160 gigabits per severed between different servers. Communication is carried out via RDMA networks. The bandwidth is relatively lower, around 50 gigabit. DeepEP leverages the characteristics of these two networks through intelligent routing strategies and pipeline design. In addition, DeepEP also supports 8-bit floating point (FP8) computation, which is a very practical optimization. Compared to traditional 32-bit floating point numbers, the data size is directly reduced by 75%. This is like using an efficient compression algorithm when transferring files, which not only speeds up the transmission, but also saves storage space. Although there will be some loss in precision, it is often an acceptable trade-off in practical applications. From the actual test data, DeepEP's performance is quite impressive. In an environment equipped with H800 GPU and CX7 InfiniBand network cards, the intranode communication speed reached 153 to 158 gigabytes per second, almost touching the hardware's theoretical limit. The internode communication speed can also be maintained at 43-47 gigabytes per second. It is particularly worth mentioning that in low latency mode, the response time can be as low as 163 microseconds, which is a good choice for applications requiring real-time responses. Of course, To fully leverage the performance of DPP, there are certain requirements for both hardware and software environments. Firstly, a GPU with the Hopper architecture is required as the hardware foundation. The software environment requires Python 3.8 or higher, CUDA 12.3 or higher, and PyTorch 2.1 or higher. In terms of network configuration, it primarily supports InfiniBand networks and theoretically also supports ROS networks. To achieve optimal performance, it is recommended to isolate different traffic types using virtual lanes. Overall, DPP is a specialized tool focused on addressing expert parallel communication issues in the training and inference of large language models. It performs well in both performance and flexibility, especially in intranode communication where it nearly reaches the hardware's limit. For teams planning to deploy large-scale hybrid expert models, this open-source project is worth in-depth study. However, it should be noted that due to its high requirements for both hardware and software environments, careful evaluation of one's infrastructure is necessary before practical application. If conditions are not met, it may be necessary to consider other alternatives or perform necessary hardware upgrades. This ensures compatibility and optimal performance.